Hi, in this video, we will discuss the application of Laplace transform. So this is the Laplace transform application, and it can be used for the first application, which can convert the complicated equation into algebra equation. So complicated equation here means you have the differentiation or you have the integration, which take a long procedure to solve it. Algebra equation here simply means you can just solve it by plus, multiply, minus, or divide. In Engineering Mathematics 1, you learn how to solve the ODE. However, the procedure is long. So in this study, you will learn a new method which involves the Laplace transform, and you will find that in this method, you can solve it much easier because you convert the differentiation into plus, minus, multiply, and divide. So this is algebra equation. Not only that, but also for the second case, you have the integral equation. Third case, you have the integral plus the differential equation. Lastly, you have two or more ODE. So this is known as system of ODE. So you will learn how to solve this equation by using the Laplace transform, and this is the main focus in this study. Laplace transform is also useful in the signal processing application. So in this case, we are going to process the original signal, which is ft, and convert using Laplace transform to obtain the fx. By doing this, we are able to obtain some useful information in the Laplace domain. So this is for your additional knowledge and is not covered in this study. So let's say you have a mass spring system where you give some initial displacement and release the system. By doing this, you obtain the response to be like this. So you can see over the time it decay to 0. So you see the thing is oscillating with some frequency omega d. So you have the term sine omega t plus beta. Beta is the angle. And also you have the decay function exponential negative sigma t. Let's say we give some value inside, okay, where you have the amplitude to be 5, your beta phase is 0, and your omega d is 2, and your sigma is 5. So when you plot it, you found that your signal looks like this. So this is your xt signal. So it's very hard for you to tell what is the frequency, and also it's hard for you to determine what is the decay rate based on this. So if you have some measurement like this, you can use the Laplace transform and convert it to S domain or the Laplace domain. So you can have the magnitude plot, and you will find two peaks indicating the pole, which is x equal to -5 plus minus 2i. If you view this plot in the top view, you will see the pole is located at omega d equal to 2 and omega d equal to -2 in the imaginary axis. And also your real part at sigma equal to -5. The pole is indicated by the x symbol. So this pole carries important information for this omega d and sigma, where you can see that the sigma is equal to -5 here, and your omega d is equal to 2, where the plus minus indicating the direction for the rotation, either it is counterclockwise or clockwise. So in summary, we can obtain the useful information in the Laplace domain, and the pole gives us important information such as the decay rate and also the damped natural frequency omega d. In this case, we have the force vibration, where you can see P cos omega t can represent a motor force acting on the system. And due to this force, you will obtain the response by the x transient and also the response by the x steady state and the total force to be equal to your S transient plus the S steady state. So your S transient can be found by using this formula, and your S steady state can be found by using this. So be careful, the omega here indicating the exciting frequency from the force. And omega d here indicating the natural frequency of the system. So let's say you measure the X total to be this, and you plot the graph. And you are going to find what is the omega d, sigma, and omega from this plot. It will be very difficult for you to find it in the time domain because the signal is complicated. Let's convert it to the Laplace transform, and you should be able to obtain this magnitude plot. And you found 4 peaks. So you have 2 peaks at the poles here, s equal to plus minus 9i. Additional 2 peaks at s equal to -5 plus minus 2i. So this is the pole 0 plot, where you found that the pole here has sigma equal to 0 and omega equal to 9. By linking it to the actual scenario, we know that this is the exciting frequency for the motor force. So with that, we have the omega equal to 9 here. Then refer to the next 2 poles, we found it to be omega d equal to plus minus 2. So this is the then natural frequency for the system, and we have the decay rate equal to -5. So at the Laplace domain, we can find the natural frequency, exciting frequency, as well as decay rate easily. So this is the overall remark. So these are some of the examples how we use the Laplace transform in the signal processing in order to extract some useful information, which is very difficult to be done in other domains such as the time domain. Laplace transform is also useful in the control application. We can use the Laplace transform to identify a system whether it's stable or unstable. So let's say we have a system here where you have one object which is impacted by impact hammer here, and it will move with initial velocity, and due to the friction it will stop. So this is the behavior for the system. Okay, you have obtained the impulse response to be like this form. So when you perform the Laplace transform and obtain the pole 0 plot, so you can see this is the left side of the S-plane and this is the right side. And your pole is locating at the left side. So if you have this case, you see that stable system have all the poles located at the left side. So based on this, we can say that this is a stable system. This is because your decay rate at the left side is having the sigma equal to negative, indicating the decay rate. So your system will be stopped eventually and become stable. Let's say you have a pole 0 plot like this, and please identify whether it's a stable or unstable system. So since this is the left side of the S-plane, well, this is the right side, so you can see the pole is here, and if the pole is at the right side, it indicates the unstable system. So this is because the sigma is positive, indicating the growth rate. In actual, let's say you try to knock down an object from the hill, and you will find that this is the initial velocity, and the velocity increase over the time up to infinity, right? So this is unstable system. So you can see that Laplace transform is very useful in many applications, and you should be aware that in our study we do not cover this. This is out of scope, and we will only focus the first application.